Let's talk about a really fascinating problem that pretty much every major tech company has to solve. How do you add or remove servers from a massive system without, well, causing a complete meltdown? The answer is this incredibly clever idea called consistent hashing. And trust me, understanding how it works is going to change the way you think about scale. Seriously, just imagine this for a second. Your service is blowing up. Things are going great, so you add a new machine to handle the load, and suddenly, everything breaks. Poof. User sessions are gone, data can't be found, your cache is basically worthless. It sounds like an absolute nightmare, right? But it's a very real problem if you distribute your data the wrong way. So, to really appreciate the genius of the solution, we first have to understand the headache. We're going to start with the most common, most intuitive, and ultimately most flawed way to spread data across a bunch of servers. Okay, so the most straightforward way to do this is something called the modulo method. First, you hash a key, which is really just a fancy way of saying you run it through a function to turn it into a unique number. So let's say our key user 123 becomes the number 1876. Then you use the modulo operator, which just gives you the remainder after division, to pick a server. With 3 servers, 1876 divided by 3 has a remainder of 1, so it goes to server 1. Easy, right? It's super fast, super simple, but it has a fatal flaw. What happens when a server goes down and now you only have 2? This right here, this is the catastrophe. That same key, 1876, when you use modulo 2, now maps to server 0. And it's not just this one key. Because the divisor, that number of servers, has changed, almost every single key in your entire system now maps to a different server. You have to move pretty much all of your data, all at once. For something like a distributed cache, this is a total death sentence. So how do we fix this catastrophic reshuffling? Well, we need a much more elegant approach. And it all starts by getting rid of that simple division, and instead, thinking in a completely different shape, a circle. And that brings us to the core idea of consistent hashing. Instead of just treating our servers as a number to divide by, we imagine both our servers and our data living together on a continuous circle. This simple shift in perspective is what prevents that system-wide panic when a server comes or goes. So let's build this up from scratch. Forget about servers and data for just a moment. I want you to just picture a ring. It could be a clock face or a big circle with numbers from 0 to a billion, maybe even a Ferris wheel. This is our new landscape. Okay, you got the ring? Good. Now let's take our servers, server A, server B, server C, and we'll give each one its own spot on that ring. We do this by hashing their name or IP address to get a number, and that number corresponds to a position on our circle. All right, our servers are on the ring. Now we do the exact same thing for our data. We take a key, like a user's session ID, we hash it, and boom, it lands on its own spot on that very same circle. So now we've got both servers and data points scattered all around the ring. Now here is the simple, brilliant rule. To figure out which server owns a piece of data, you start at the data's position on the ring, and you just walk clockwise until you hit the very first server you find. That's it. That server is the owner. It's a beautifully simple and totally predictable system. Okay, that sounds great, right? But there's a potential flaw in this elegant system. Hashing is random. So what happens if our servers don't spread out evenly on the ring? Exactly. You could get really unlucky. What if server A and B land right next to each other, but server C is way over on the other side of the ring? Well, that means server C becomes responsible for this massive chunk of the circle, while A and B are barely doing any work. The load becomes dangerously unbalanced. And here's the trick that makes this whole thing production ready: virtual nodes. Instead of placing each physical server on the ring just once, we pretend each server is actually, say, hundreds of virtual servers. So we give server A many different positions, and server B gets a bunch of positions, and so on, basically sprinkling them all over the ring. And the difference is, well, it's night and day. On the left, without virtual nodes, you can see one server gets stuck with a huge slice of the pie. But on the right, with virtual nodes, each physical server now owns lots of little, tiny, distributed slices of that ring. It's really just the law of large numbers in action. You add enough random points, and everything just smooths out, making the load incredibly well balanced. So now that we have a balanced ring, let's go back to our original crisis. What actually happens when we add or remove a server from this new system? This is where we see the real magic. Let's add a new server. server D. We sprinkle its virtual nodes all over the ring. Now, watch what happens. The only data that needs to move is the data that now finds one of server D's nodes as its new closest neighbor clockwise. Everything else on the ring, totally unaffected. The disruption is localized and absolutely minimal. And the same beautiful thing happens when a server fails. Let's say we remove server B. All of its virtual nodes just disappear. The data that used to be owned by server B simply gets handed off to the next server clockwise from each of those points. Again, the blast radius is contained. No catastrophic reshuffling. And this minimal disruption isn't just a feeling, we can actually quantify it. When you add or remove one server in a system with n servers, you only need to remap about 1 divided by n of the keys. So think about it. If you go from 100 to 101 servers, only about 1% of your data needs to move. It's a world away from that everything moves catastrophe we saw with the module method.
Now, this isn't just some cool theoretical computer science concept. This is the bedrock of how so many of the largest distributed systems on the planet actually achieve stability and scale.
You will find this thing everywhere. Amazon's DynamoDB uses a form of it. Load balancers use it to make sure your requests keep going back to the same server, what's called a sticky session. Anytime you need to slice and dice data across a fleet of machines that might change, consistent hashing is almost certainly part of the picture. So let's look at the trade-offs, right? That simple modulo method has what's called O of 1, or constant time lookup. Basically, it's instant no matter how many servers you have. But the disruption is catastrophic. Consistent hashing is slightly slower, what we call O log V, or logarithmic time. All that means is the lookup time grows very, very slowly as you add more virtual nodes because you have to search the ring. But in return, you get that minimal 1/n disruption. And there are even newer methods like Google's jump hash that manage to get the best of both worlds, though they come with their own different set of constraints. Look, if you remember just one thing from all this, let it be this. It's all about mapping your servers and your keys onto a ring, using virtual nodes to keep things fair and balanced, and the result is that you only have to move a tiny, tiny fraction of data when your system changes. That's the core of it. And that kind of leaves us with a final thought. This was a hugely complex problem of system stability at massive scale, but the solution was based on a simple, elegant geometric shape. It really makes you wonder, doesn't it? What other massive challenges in computing are out there, just waiting for an equally elegant and simple idea to come along and solve them?